now. So how do we want to sort of attack this? Well, we started off the very first class talking about what is calculus, and we mentioned some things like I tried to stimulate your mind about that particular question by asking about two sort of ideas or things: area and velocity. These are words that we use every day in the English language. But what's interesting is that we often don't really understand how to define them. So that sort of was the motivating factor to what calculus is all about. And so what we'd like to do today is we would like to think about these topics in a slightly different perspective. So that's what we're going to do now. So let's sort of think of it this way. So the fundamental idea behind calculus is what's called a limit. So as I alluded to, sort of humans have had this idea of how to study area and not necessarily velocity and speed right away, but we eventually gathered that. But the missing piece to the puzzle of bringing these ideas into a solid framework was this thing called a limit. So what we'd like to do is we'd like to investigate it in two particular examples, and in these examples will help illustrate what we're going to be doing. So let's consider the following. So let's take the function f of x equals x squared and look at the region bounded by its graph on the interval 0, 1 and the x-axis. So let's draw that. And we'll do that on the next page. So I am interested in studying the following. So if this is height 1, this is height 1, we know x squared goes through this point 1, 1. And the graph is going to look something like this. So what I'd like us to consider is if this is the parabola x squared, what I want to restrict our attention to is this region right here. That I'm shading in pink. And so what we'd like to ask is we would like to ask, what is the area of this pink region? So this is a very natural question. maybe you don't care about the question, but you can at least imagine that a human being would be curious. What is the size of this region? So, long time ago, many smart people tried to answer this question. And if you believe written history, the first person to actually sort of make sense of this problem was a guy named Archimedes, who maybe you heard about when you were in primary school geometry or science class. So one way we can attack this problem, at least using our modern language of algebra, is we can say, okay, I can't necessarily have an instant answer, but I can use deductive reasoning to maybe investigate. And then along the way, this investigation might yield some new ideas, and then these new ideas might help me solve the problem. So one idea to do this is try using a known idea to answer questions about a new idea. So what we can do is let's start by using rectangles to approximate the area. Now you might say, well, why would I think of that? Well, again, I'm not saying you would think of that, but I guarantee you, if I told you I'm going to give you $1,000, if by tomorrow you can come up with your own way of determining the area of that, but I didn't give you any technology. I locked you in a room and I said, here you go. You have a paper and you have a pen. Go to work. I think eventually you might come up with this idea, especially if you really wanted to win $1,000. This idea would not be obvious at first, but even though it might not be obvious at first, it might be something that after some brainstorming or discussion amongst someone else, you might come up with. Now, there's lots of ways I can do this, but here's a very systematic way we can do it. So I'm going to go to the next page and draw a much bigger version of this picture. And it's a good possibility that many of you have seen these ideas before, and that's good. And I'm going to be very careful with how I graph this guy this time. So I'm going to think about how I might do this. What does the graph of this creature look like? Well, it's going to go through these 3 points. This is the point 1, 1. This is the point 3/4, 9/16. This is the point 1/2, 1/4, etc. And if I go back to my blue pen, and what I'm going to do is if I get my pink, I'm going to remind myself that what I was trying to do was this pink region. But instead of shading it in, what I'd like you to do is instead draw some rectangles. So I'm going to draw 4 rectangles here. I'll do it in purple, and I'm going to draw them in a very specific way. And the reason I'm going to draw them in a specific way is because then I immediately know what the height and width of each rectangle is. So I'm going to draw this rectangle here. I'm going to draw this rectangle here. I'm going to draw this rectangle here, and I'm going to draw this rectangle here. So the 4 rectangles have the following total area, which I'm going to give a name to. I'm going to call it A. Well, let's be a little more clean with it. I'm going to call it A sub 4. So this subscript of 4 is going to tell me that I have 4 rectangles. And so notice the width of every one of them is 1/4. Notice that's the width of every one of them. And so if the width of every one of them is 1/4, I can pull that number out. And then what I'm left with are, what are the heights? Well, the height of the first one is 1/16. The height of the second is 1/4, but another way of writing 1/4 is 4/16. The height of the third is 9/16. And the height of the fourth is 1, but another way of writing 1 is 16/16. So this might take a moment for you to capture, but I'd like you to make sure you understand this. And then I'm going to do some calculation that I'm not quite sure you're most of us at first are going to say, why are you doing this way? Some of you are probably thinking, why don't you just plug it into the calculator and get an answer? Well, I could, but then if I do that, I miss this pattern. I miss something that's very nice that's happening. So what I'm going to do is I'm going to recognize that every one of those guys has a 16. So I can factor that out. And 16 is the same thing as what? It's the same exact thing as 4 squared. So if I pull that out, I have a 4 cubed downstairs. And then what I'm going to do is I'm going to write the numerators so that I see a very particular pattern. Does anybody have a question? Excuse me. Okay, now, I'm going to compute this number, and you can use a calculator to do it if you'd like. Uh-oh. Drama. Sounds like my house. So if you go to a calculator and you sum some things, depending on so bear with me 1 second. I hit the wrong button on my calculator. So what you end up getting if you sum this is you get the following. Sorry. What you end up getting is you get 15 divided by 32. Which you can write in decimal form. As 0.46875. So what I'd like you to do is I'd like you to think about that calculation for a second. And if you have a question, please ask. You can ask them any way you'd like. Any questions? All right, so now if I look at this, it would not be hard for me to get some ideas from this. There's nothing special about 4 rectangles other than it's easy for me to draw. That's it. There's nothing special about it other than that. It's easy for me to draw. Okay, so what I'm going to do then is I'm going to note, if I look at this sort of line of reasoning, I can extrapolate a general formula from this. So let's look at that, if we will. So we can repeat this for any number of rectangles. You know, for example, if you have n equals 10, then a sub 10 would be equal to 1 over 10 cubed times 1 squared plus 2 squared plus 3 squared all the way out, and you would stop once you got to 10 squared. And what you might want to do is draw this so that you can verify it for yourself. You know, for n equals 50, I would have 1 over 50 cubed times 1 squared plus 2 squared plus 3 squared all the way up to 50 squared. And by the way, I can, with a calculator, readily compute these values. It's not difficult to do that. So for example, if I went to a calculator, I can determine that this number is approximately 0.385. And if I went to a computer and got the next one, I would get that this number is approximately 0.3434. And then why stop at 50, since we have calculators and computers at our disposal, we can add these things up. And later in the semester, I'll show you how to do it. That's not the important thing right now. If I do it for 100, I get 1 over 100 cubed times 1 squared plus 2 squared. And then, of course, this pattern continues all the way out to 100 squared. And when I do this, I notice something. I notice, okay, that if I look down the list, these three values that I computed both share the same tenths value. They both have a 0.3. So we're going to dive into that a little deeper in a second. Does anybody have a question about this? Comment, concern? All right. I'll assume you're all enthralled by this. Okay, good. So let's now go a little deeper. Instead of doing it with 1,000, or excuse me, 100, let's ask what happens if we use 1,000. Now I'm going to save all I'm not going to keep writing all that out. But if I do 1,000, what I find is these sum of the rectangles, their area is 0.3338335. So there is a moral. What you'll notice now is that if I read down the list, I started with them just agreeing to 1 decimal place. But now what I'm finding is the last two agree to not just 1, but 3 decimal places. So let's sort of summarize this little experiment on the next page. So what I'm going to do is I'm going to make a table. I'm going to make a table. We'll call this side n. That's the number of rectangles. And we'll call this guy a sub n. That's the area of those rectangles. And so we computed some of these. It's worth reminding ourselves what they were. So the first thing we did was we computed 4. And so when n is 4, we found this number 0.46875. And then we did 10. And, oops, hold on, I just messed up. I messed up my calculator, my apologies. So when we did 10, you'll recall we got 385. And then we did 50, and when we did 50, we got .3434. And then once we did 50, we did 100, and we got .33835. And then we did 1,000, and we got .333833. And so the point I'm trying to make is that we're starting to recognize a pattern. So what if I went to, instead of 1,000, what if I went to 5,000? Well, if I do 5,000 rectangles, if I do 5,000 rectangles, I get .333433. And then if I do 10,000, if I do 10,000, I gain an extra 3. So if we look at this chart and we study it, what we see is we see a very beautiful pattern. And if our minds are interested in patterns, we'd like to figure out how to sort of make more detailed sense of it. And by the way, you guys should all flunk me. Look at me. I'm turning in the sum of u. This is not R. What kind of terrible grammar is this? This is our findings. Oh my God, I should be fined for such terrible grammar. So what is this table suggesting? Well, if I read down the left-hand column, as n gets larger and larger and grows without bound, a sub n seems to, what we would say, approach one-third. I don't think you would argue with me that that's what we're seeing there. Why do I say one-third? Well, you guys will recall that one-third is .3333 and goes on forever and ever and ever. Does anybody have a question about this chart? All right, now I'm going to show you a visual, and then I'm also going to show you sort of how we made this happen, how I computed these so quickly. It's not hard to do. You can even learn it on your own. Okay, so if nobody has a question, I'm going to switch to a different screen to help get a visual for this. So what I'd like to do now is ask you to check out this page. So the web page I'm using here is another sort of thing like Desmos. It's called GeoGebra, and it's free, and it's real easy to learn. And the first thing I want to show you is that it will easily calculate the area of these rectangles. It has a built-in function. So you might look at this thing on the left-hand side and you'll recognize the function, but you might be afraid of this rectangle sum business. That's just built-in code that does all the arithmetic for us. It adds up the area of these 4 rectangles. And you'll notice that this number here, this 4 that you see in here, that means I'm going to use 4 rectangles. And you'll notice that they got the same number we got, 0.46875. Now, what I'd like you to do is think about the visual of what happens. If I, instead of using 4, if I use 10, if I use 10 rectangles, even to our eyes, the approximation should become better because we are cutting out air. So for the sake of argument, if I go back to 4 rectangles, if you can see where my mouse is moving, this part of the rectangle, this part of the rectangle, and this part of the rectangle, and this part of the rectangle are overestimating the area under the curve. So what happens as we increase the number of rectangles is that area shrinks. Because when I increase the number of rectangles, by default, the widths of them have to shrink. And so if I go from, say, 10 to 50, you'll see that now to your eyes, you know, if you pull your eyes far enough away from the screen, you might not even recognize that there are rectangles there. By the way, you'll match this up. If you compute the area of the 50 rectangles, we got 0.3434 for the area of the 50 rectangles. And now, if I go from 50 to 100, once again, your eyes, the blur is starting to almost insinuate that we're no longer using rectangles, but we are just shading in this curved region. Now, of course, if I zoom in a little bit, then I start to see my rectangles pop up again. Now, if I go from 100 rectangles to 1,000, you would have a hard time convincing someone who just walked in right now and looked at the monitor that there were 1,000 rectangles right there. Right now, what you're seeing is you look like you're seeing a blue region that has 2 straight sides and 1 curved side. Although we know, because that we're doing this, that one side is not curved. It's in fact the tops of 1,000 rectangles. But to our eyes, we are deceived. And by the way, it should be pointed out for context, this is really the general idea behind how lots of technology works. This is how monitors work. This is how movies work. Do you ever really think about how a movie works, how video works? If you do a little research, you'll notice the first movies were called motion pictures. And the reason they were called that is because they were on reels, a big reel, and they were lots and lots of pictures. And if we move the circular reel fast enough, our mind is confused into thinking all those pictures are moving. And this is precisely what's happening right here. That is a blue region that to your eyes looks like one side is curved, but we know it's not, because we know if we zoom in enough, and the graphics don't fail us, if we zoom in enough, these are really not curves, they're these tiny little tops of rectangles. The widths of each one of these rectangles is 1 divided by 1,000. What happens if instead of 1,000, I do 2,000? Well, it shrinks. What if I say, okay, let's do 3,000? That area shrinks some more. So as I keep increasing the number of rectangles, their widths must shrink. And then when I zoom out, it is very hard to convince someone that there are rectangles there. If someone just walks in the room, as I said before, they are not going to believe you that there are 1,000 or 3,000 rectangles. They're going to say that is a curved region. That's what they're going to say. Does anybody have a question, comment? Okay, so fair. So let's go to share. Let's go back to our whiteboard. Questions, comments? Okay, so actually, it might be wise to give you one more example of this idea, the geometric visualization. So let me actually go back to the internet. So a couple years ago, I wrote this in Desmos. It helps you, the student, understand some more ideas of what we call these limits. If you look at this picture right now, you should see a blue circle with a triangle inscribed in it. And then you can see a blue circle with a pentagon inscribed in it. And this is another one of Archimedes' ideas. Archimedes wanted to study circles. So what he did is he realized that he can inscribe polygons inside of circles. And as he increases the number of sides, the polygon begins to resemble more and more a circle. Right now, it looks like you have a purple circle, but you don't. You have a blue circle, and then also you have inscribed in that blue circle a polygon with 30 sides. As I increase the number of sides, my polygon begins to resemble more and more a circle. Okay. Sure. Does anybody have a question about this? All right. So, okay, back to the whiteboard. So, what we want you to understand is geometrically, what we have is we have a couple things happening. We are using straight lines to approximate curves in two different ways. And then not only are we doing that geometrically, but we realize if we compute numerical sort of the quantities about these lines and curves, what we're realizing is we have a pattern. So if I come back here, it makes sense to write, and we're going to explain this notation in detail. So what this does is this suggests notation. It suggests writing. And we're, again, what we do is we write this LIM, and then we're going to write N with an arrow, and we're going to use this infinity sign. It suggests that we come up with notation for this. So this is sort of a mathematical way of writing that as we increase the number of rectangles over and over again, the more rectangles we add, the closer their area is going to be to 1/3. And so not only does it suggest we create this kind of notation, but it also suggests that we that if we're going to define area later, that this might just be the way to do it. Okay. Does anybody have a question? All right, bear with me for 5 seconds. I gotta do something real quick and I'll be back. Sorry about that. We have multiple. Amy's got a Zoom meeting and she couldn't log in. All right. So where were we? Okay. So let's kind of reset. Don't get overwhelmed by this notation yet. We're going to explain it as the days go on, but we just want you to get an idea for why we're going to write these things later on. Okay. Let's look at another motivational factor of a different problem. So okay, so so it's well known, and we will see why later this term, that an object that is projected straight up and falls straight down can be described by an equation that is quadratic. So what I'd like to do is I'm going to write this as a function. I'm going to write height, its height at any given time. Might be given by a function like this. This is a quadratic equation. So a long time ago, some smart people like Galileo realized that falling objects sort of obeyed that their distance traveled or their displacement or the height at any given time was proportional to time squared. And then if you use Newton's laws, you can derive the general form for anything that is shot straight up and falls straight down. And you've probably seen this in an algebra class before. They did examples where they might have asked you how long does a toy rocket stay in the air if it's projected straight up, stuff like that. Okay, so the question is, what is the velocity of the rocket at any given time? So if you go back to the first day in class, I said there's two historical problems that sort of forced human beings to either invent or discover calculus, depending on how you want to think about it. And area was one of them. It's the classical example, dates back to the beginning of written history. And then the problem of speed and velocity, which was finally resolved officially with Newton in the 1600s, I guess if you believe the history books. So the question is, how do we study this creature, and how do we define velocity? So what we would like to do is we would like to ask, okay, if I shoot something in the air, or I throw something in the air, or I launch something in the air, how fast is it going exactly 1 second when it leaves? I don't know, maybe you guys watched last Saturday the rocket ship that went in outer space, and if you were paying attention, some of the broadcasts of that had some pretty cool things, like they were showing you the speed at any given time and the altitude and all that stuff. How do we do that? How do we define those things? How do we make sense of all that? So one way to sort of analyze this problem or make sense of it So one idea is to start with what we call average velocity. So we'll give this a name. We'll use V with the subscript AV. And what we'll note is the average velocity. Think about what would be a nice way to define velocity. Well, if you took a physics class, you would already know this. But if you haven't taken a physics class, we as humans have to come up with a definition of average velocity. And so what we do is we define velocity as our change in displacement over time. We take two instances in time, we look at where we're located, we compute the difference of that, and then we divide by how much time. Many of you have probably done this in a car and you haven't even thought about it when you're going on vacation or traveling somewhere. So average velocity is defined as height at time 1 minus height at some other time, which we'll denote t0, all over the distances, or excuse me, the difference in those times. So if you want, this is just change in displacement over change in time. So what we'd like to do is we would like to sort of use this idea to get information about what's happening when one of those instances in time is the number 1 second. Now, this average velocity is not a new friend. You've seen this before. This average velocity is just another way of writing your difference quotient. That's all it is. It's a difference quotient. Draw it. It's a difference quotient. So if we draw a picture, which we know O'Grady likes to do, so if we go back, by the way, what was our function? It was negative 16, 90, and 5. So if I'm just going to sketch the graph of this. This is a parabola that's upside down. And you guys would recall, with maybe some help from your algebra days, that its graph is going to look something like this. You know, we call this the vertex. Call this the x-intercept. So this parabola helps us describe how our object goes up and then falls back down. So if we look at the point 1, which I'm going to draw this not really to scale so that we can sort of think about it. This would be the point 1, comma, h of 1. Now, let's pick some t, or pick a number that's a little bigger. So let's pick, I don't know, let's compute average velocity for some time intervals. So let's think about it. Let's do 1, comma 3, 1, comma 2, 1, comma, say 1.5, 1, comma 1.1, 1, comma 1.01, etc. So let's compute the average value of, excuse me, the average velocity of our height function on these time intervals. And by the way, for example, if I call this the point, say 3, then the average velocity is nothing more than the slope of this line. So let's make sure we're all aware of that. So the slope of the pink line is just the velocity, or the average velocity, on the interval 1 to 3. So what was your average speed, if you will, from 1 to 3 seconds? So once again, let's make a chart. Let's make a table. So we'll start here with times. Or let's not call it times. Let's say the interval. So we'll write it 1 comma t sub 1. And then we'll put the average velocity in this column. So the first one we want to do is 1 comma 3. Now, I'm not going to go through all these, but it's real easy to do. So what is it for 1 comma 3? For 1 comma 3, the average velocity is h of 3 minus h of 1 all over 3 minus 1. And you can easily go to a calculator to make this happen, or you can do it by hand, whatever you prefer. That's up to you. But you should, whether you use technology or not, what you should do is you should absolutely know how to do it by hand. So don't forget what h is. If we go back, it's negative 16 plus 90, negative 16t plus 90t plus 5. And so if we plug those values in, what we find is the following. So if I plug in 3, if I plug in 1, so just to do the first one, we'll beat the dead horse on the first one. This is 131 minus 79 over 2. Which is 52 over 2. And what's 52 over 2? That's 26. So we get 26. And if you want, well, we'll leave units out of it for a second. But if you want, what this is really in is this is in feet per second. So let's just look at the average velocity, which is 26. So before I do anything, does anybody have a question about this? Going once, going twice. All right, so then the next thing we want to do is we asked what happens if we go from 1 to 3. What if we shrink that time interval down? What if we shrink that time interval down and just consider what happens from 1 to 2? Well, if I compute this, we get that our average velocity is 42. And then the next one was what happens if I shrink it down to from 1 to 1.5. Well, if I do that, plug it into my calculator, I get that now it's 50. And then the next one I wanted to investigate was 1.1. So if I compute my average velocity from 1 to 1.1, now I get 56.4. And then let's do 1.01. So when I do that guy, I obtain 57.84. And then for fun, let's just keep it going. What if I did 1.001? Now what I'm seeing is a pattern. Now I get 57.984. If I do some more, what if I do 1.0001? If I go to my calculator and compute that, I now get 57.9984. So if I continue this experiment, what I'm going to arrive at is something very interesting. What happens? Well, if I look at this and I go back to what we're seeing before, let's write this down in a slightly different manner. So, observation. As t gets close to 1, h of t minus h of 1 over t minus 1 seems to get close or approach, if you will. If you look at this, if you continue this investigation, you're going to get 57.99 and then 57.999 and 57.999. So really what that is the number 58. Does anybody have a question about this? Again, if I go back to the previous page, if I keep the same pattern in the left-hand column, the right-hand column is going to get closer and closer to 58. If you don't believe me, do it. So all these words I'm putting in quotation marks, and these sort of very generic English words, get close or approach. We have to sort of make this all more precise, and that's what we're going to do. But what I'd like you to think about is that this investigation suggests two things. And here's what I want you to do. I want you to ponder this. First, it suggests new notation. We write limit as t approaches 1 of h of t minus h of 1 over t minus 1, that we might write this as equal to 58. And the second thing it suggests is we can define what's called instantaneous. So if we talk about these limits that we sort of foreshadow, remember, if you go back, I haven't defined what a limit is yet. I'm only trying to motivate them. I'm only trying to motivate them. And what this sort of investigation, along with the previous investigation, what they do is they help facilitate some idea of how do we quantify a pattern we see happening. We see a clear pattern, how do we quantify it? And it turns out that the way we're going to quantify it is through this idea of a limit. And then this limit is going to be super important because it gives us a means to defining things. The limit is going to be the key to defining velocity. That's what I'm telling you here. The limit is going to be the key to defining area. We'll see that later in the semester. Does anybody have a question about this? All right, any comments, questions? So let's actually say something. I don't want to call it the third thing because it's really more generic than what we did before, but more is true. So the reasoning above has a geometric interpretation. So the limit of the, again, I'm putting limit in quotations because we haven't defined it yet. But the limit of the average velocities is the slope of the line tangent to the curve at the given point. So let's go to a picture to see it. And again, please, if you have a comment, if I'm going too fast, if you're curious about something, just speak up or stay asleep. I don't know. However you want to do it. So what do I mean by this limit of average velocities? Well, let's go look at Desmos. So what I'm going to do is I've already have these graphed here because this is what I was using to do the quick calculations. So if I change my graph here, sorry about that. We have Kindle issues with children. The joys. All right. So look. Anyhow, what I want you to do is I want you to check this out for a second. So I am going to. Here's the function we were studying, and we were interested in what was happening at 1 comma f of 1. And so we did things like looked at the following. We looked at points a comma f of a. I was using h, but I can't use h here. Desmos wants me to use f. And what I can do is I can let this be, say, wrong. Okay, so what happens is I have this point. I was studying the green point, and I wanted to know what was the slope of the the line between the green point and the blue point. This is my average velocity. So how do I figure out what that line is? Well, that's not too difficult. I use my point slope form. So it's y minus f of 1 equals, now I need the slope. Well, what's the slope? The slope is f of a. By the way, I'm not, you don't need to know how to do all this, what I'm typing in right now. Now, if you want to learn, it's not hard, but you don't need to. What I would ask you to consider is merely consider the picture. And what I want you to look at is what happens as the green point moves to the blue point. That black line, which is touching the curve twice, begins to look more and more like it is touching the curve once. And so that is how we're going to define this geometric notion of the tangent line. And the slope of that black line will also be how we define velocity. So this is the geometric interpretation. As the green point moves, as the intervals I study shrink down to nearly 0, or 0 for that matter, we get a tangent line. Okay. Does anybody have a question about this? Comments, concerns? All right, so here's what we have to do moving forward. We need to make the above ideas precise. And to do this, we need to start by defining what's called the limit. All right, so here we go. So suppose f is defined on an interval containing the point A, or the number A. We do not require f of A to be defined. So it can be, if I have an interval that contains A, all I'm asking is that it's defined around A. It could be defined at A, but it doesn't have to be. Now, that might not really make much sense to you right now, but soon enough it will. So assume we can make I don't want to say assume. That's very poor language. If we can make f of x arbitrarily close to some number L, by choosing x sufficiently close to A, we say the limit of f of x as x approaches A is L, and here's what we write. So this is a whole lot of crap thrown at you. Now, even though it's very it seems overwhelming, all these words, the intuition is very clear. It's just very difficult to define. And in fact, this is really sort of like a non-technical definition. We can make all this language precise in a second. So a good way to think about this from a naive standpoint, which will rarely get you into trouble, so here's the key idea. This set of symbols means f of x close to L when x is close to A. So output close to L when input close to A. So if you take a moment to think about it, this is actually getting to what we set out to study and what we talked about the very first class. The very first class we talked about this idea of change and this notion of what happens to the one quantity when another quantity changes. Well, that's what this is quantifying. That's what this is telling us about. It's saying if one quantity, the input, does something, how does that affect the other quantity, which we call the output? So what happens to the output of a function, or what happens to one quantity when the input is near some particular value? That's what this is sort of measuring or quantifying or describing. What does the behavior of f look like when the inputs are close to A? That's what we're trying to get to the bottom of. Does anybody have a question about this? So I should make a note because it's fair that we say this. So the definition above can be made rigorous. However, to do this, what we require is an understanding of what we call propositional logic. And most students in Calculus 1 don't have that because you haven't taken courses that study that yet. So this is usually left or usually used in advanced courses. Now, if you're curious to what it looks like and you want to see it, go see your book at the end of chapter 2 actually does it. It talks about this idea of what we call the rigorous definition of limits. But we're not going to deal with that in this course. I guess I should spell understanding correctly so you don't fire me. No, we don't require is, we require an. By the way, if you're curious, it looks something like this. So how do we measure distance of numbers? Well, we use absolute values. It means the following. So it means for any number you choose, we typically use this Greek letter epsilon. Then we say there exists some other small number, which we reserve the letter delta. Such that the distance between f of x and L is less than epsilon when x is arbitrarily close to A. So that is scary looking stuff. If you want to dive into it and ask me questions about it, I would be happy to do it. We're just not going to say anything else about it the rest of this semester. Okay. So if we're not going to say anything about this, why do we care so much about limits? Well, there's, as I said earlier, they're the fundamental, they're the foundation of calculus. And so that might sound confusing if I just said we're done with that definition. So our job in this class so we need to be able to compute limits graphically and symbolically. We're not worried about the theoretical aspects of limits in this class. So that is what your next assignment is going to be about. It's going to be about how do we compute limits? How do we understand certain sort of properties of limits, and what information can we gain by studying the limits of certain functions. So with that said, I think this is a good place to stop, because you need to maybe watch this again and maybe do these investigations on your own, and then I'm going to submit or post your next homework, which is going to give us sort of an idea of how we're going to handle limits, and we'll talk about those problems on Tuesday. Hopefully you'll have questions, and hopefully it'll be a good learning experience. So if you guys don't have any questions, I say I will see you Tuesday. Does anybody have any questions? Someone's chopping up. Yep. Okay. So if there are no other questions, or if you want to just ask me a question via the chat, I'll stick around, but I'm going to end the recording now. And so if you have a question, stick around and let me know. If you're going to leave, have a good weekend, and I'll hopefully hear or see from you Tuesday.